Hello, students. Your teacher here, Mr. Sirosinski, and this is an episode of STC Prob and Stats, and we are in Module 3, Probability, and this is our last lesson, 3.5, on tree and Venn diagrams. In this lesson, I'm going to have a couple warm-up problems. One is from the notes from 3.3, example 9, and one is from the homework, and it's just another example of the two-part question from the homework where you had to find the probability of all three marbles being the same color, but you weren't told which color. And it was kind of a long problem that I think a lot of people will need some help with. And a couple examples from the notes, and you guys will finish up this lesson with practice on My Open Math for lesson 3.5. So let's go. Starting out with example 9 from lesson 3.3, where we were finding probabilities using the two rules. And this example uses a lot of complements, and I thought it would be a good example to go through together, even though we weren't able to get to this example in the notes. So it is asking us to refer to example 8 that were in the notes, and so some of the information that I get for this is going to come from that. All right, so the probabilities that I needed from the other example were this. First, we had the probability of a woman who is 90 years or older of getting breast cancer, and that was 0.143, 14.3%. The probability of a negative test given that you have breast cancer, they said, was 0.02. And then the probability of not having breast cancer is 0.85. Okay. So in part A, it says, given that a woman develops breast cancer, what is the probability that she tests positive? And it even does a great job of helping us know how to find these values. And it does this in each one of the examples, and I really appreciated that here. So for this example, if the probability of a negative test, given that she has breast cancer, then this is just the complement to that. So the probability of a positive test, given that she has breast cancer, is equal to 1 minus 0.02, which is 0.98. Part B, what is the probability that a woman develops breast cancer and tests positive? And it tells us to find B and P, and that is equal to the probability of P given B times the probability of B. And since we just found the probability of P given B, then we should be able to solve for B and P. So we have 0.98 equals the probability of B and P all over the probability of B, which is 0.143. And in our lesson from 3.3, we used the multiplication rule here to solve. And all I have to do is multiply both sides by the probability of event B, and I get 0.1401. All right, C, what is the probability that a woman does not develop breast cancer? And this is the complement to event B, or B prime. And it tells us that the probability of B prime is equal to 1 minus the probability of B. So 1 minus the probability of B, 0.143, is equal to 0.857. And our last part, what is the probability that a woman tests positive for breast cancer? And it even tells us that this is 1 minus the probability of a negative test. And so the probability of positive equals 1 minus 0.85, which is 0.15. Okay. Next example. And for all of these, I encourage you to pause the video, read through the problem, and see if you can get the answers yourself before you click play. All right, so for this one, we had an urn containing 10 red marbles, 10 white marbles, and 5 blue marbles. A child randomly selects 3 without replacement, and that's important, from the urn. Round to 4 decimal places. So first, find the probability that all 3 marbles are the same color. And in this example, we have a sample space of 25. And the probability of red is 10 out of 25. The probability of white equals 10 out of 25. And the probability of blue equals 5 out of 25. So the probability that all 3 marbles are the same color, and this is without replacement, so each time we're reducing the sample size and the number of items that we have, or the number of favorable outcomes. And so we have a pretty big problem here. And so for red marbles, in order for each one of them to be red, first, we would have a probability of 10 out of 25. Then, if we pulled one, we would only have 9 left, and there would only be 24 total left. And again, 8, and then 23. And so this is the probability of getting all red. Now, since we don't know which color it's wanting, we have to add this probability to the probability of getting all white, and then lastly, the probability of getting all blue. So a little bit of work to do here. We've got the same thing for white, since it actually had the same number as red. 24. And then blue. We have 5 out of 25 times 4 out of 24 times 3 out of 23. And if you do the math, and I actually use one of the little yellow calculators, you can do one group at a time and write down the answer and then add them. Just keep your answers when you multiply them in fraction form, so that you're not rounding and potentially getting the wrong answer there. But if you did that, you would get 5 out of 46, or 0.1087. Okay, and both of these solutions are verified. All right, so for part B, find the probability that none of the 3 marbles are white. And if we know the probability of white equals 10 out of 25, then the probability of not white is equal to 1 minus 10 out of 25, which is 15 out of 25. And we need all 3 of them to be not white. So the first one would be 15 out of 25, and then the second would be 14 out of 24, because remember, this is without replacement. And then the third would be 13 out of 23. And if you were to multiply those all together, you would get 0.1978. All right, now let's move on to our lesson. This is our objective. I can use Venn diagrams and lists to solve probability problems when appropriate. And I think you guys will find this lesson at least to be pretty easy. So tree and Venn diagrams. Sometimes when the probability problems are complex, it can be helpful to graph the situation. Tree diagrams and Venn diagrams are 2 tools that can be used to visualize and solve conditional problems. Tree diagrams are a special type of graph used to determine the outcomes of an experiment. It consists of branches that are labeled with either frequencies or probabilities. Tree diagrams can make some probability problems easier to visualize and solve. So here is our first example where we are using tree diagrams to find probabilities. And you can see in this example, we have a great tree diagram. It's even shaded with the first draw and the second draw. Below, it totals the number of outcomes so that you can see, when you're using these to find your own probabilities, that you will know how to total the outcomes to find the sample space. And so let's work through this example real quick. It says, in an urn, there are 11 balls. 3 balls are red and 8 balls are blue. Draw 2 balls at one time with replacement. With replacement, and you guys know what this means. And so then the tree diagram, this tree diagram shows frequencies, but all of the ones in our notes do not. It says the first set of branches represents the first draw. The second set of branches represents the second draw. Each of the outcomes is distinct. In fact, we can list each red ball as R1, R2, R3, and each blue ball as blue 1, blue 2. Then the 9 red outcomes can be written as red 1, red 2, red 1, red 1, red 1, red 2, and so on. The other outcomes are similar. There are a total of 11 balls in the urn. Draw 2 balls one at a time with replacement. There are 11 times 11, which is 121 outcomes, which is the size of the sample space. Of an example, more of a how-to. Possible outcomes for these 2 inner branches. The sample space being summed up there, but it says right here that 9 times this tree diagram filled out. Then you can see in the first draw, there's 3 reds, and we're replacing them. So then the same amount of draws are going to be possible in the second draw. It will be 3 out of 11, that's R first, and then B, and since B is replaced, this is going to be 8 out of 11. I use the tree diagram to help me a little bit here. So if we get B on the first draw, that only happens 64 plus 24 times. And none of the first draw, where B is first, have an R on the second draw. Only 24 branch. It was diagram. We had R on the first draw in the last 2 outcomes in our tree. So 24 plus 9 is 33. Second draw was 24. All right, so in this example, part A asks us to list the 24 BR outcomes, and they are blue 1, red 1, blue 1, red 2, blue 1, red 3, and since there's only 3 reds, those are all the blue ones. So then we would have blue 2, red 1, blue 2, red 2, and blue 2, red 3, and it would keep going. Now this is important just to help you visualize but we are not going to be using these right now, which is why I stopped. Okay. Part B, using the tree diagram, calculate the probability of red. And we know that it's going to be out of 121 outcomes, just based on red happens out of 121. And if you didn't have, this should be 3 times 3 or 9 out of 121. All right. For part C, using the tree diagram, calculate the probability of R then B or B then R. And the probability for R, B equals R first, then B. And if we multiply those two, we would get our probability for RB as 24 out of 121. And then again, the probability for BR, well, the probability of getting B first is 8 out of 11, and the probability of getting R second, since we are replacing, is 3 out of 11. This would also be 24 out of 121. And so, since it's impossible to get RB and BR at the same time, then the probability of RB or BR equals the sum of these two probabilities. So 24 out of 121 plus 24 out of 121 equals 48 out of 121. Okay. Part D, using the tree diagram, calculate probability of R on the first draw and B on the second draw. Well, the probability of R on the first draw and B on the second draw is 3 out of 11 for R and then 8 out of 11. And we already know what that equals. That's 24 out of 121. We just did that. Okay. Using the tree diagram, calculate the probability of R on the second draw given B on the first draw. And R on the first draw. So in this example, we're actually changing the sample space. 88 total times that happened. So our new sample space is going to be 64 plus 24, or 88. And then R on the second draw, given that B was on the first, have R second. So this would be 24 out of 88, or 3 out of 11. Part F, using the tree diagram, calculate the probability of getting B twice. And that one was pretty straightforward. The probability of B twice was the 64 out of our total sample space, 121. Part G, using the tree diagram, calculate probability of B on the second draw, given R on the first draw. And in so we're changing our sample space again. And the number of times that B was on, so this would be 24 out of 33, or 8 out of 11. All right. Example 2, you try, and I encourage you to pause and try this. Okay, assuming you paused and tried this, it says in a standard deck there are 52 cards, 12 cards are face cards, event F, and 40 cards are not face cards, event N. So we have the probability of F and the probability of N. And so F is face cards, there are 12 out of 52, and non-face cards, there are 40 out of 52. Draw 2 cards, one at a time, with replacement. All possible outcomes are shown in the tree diagram as frequencies. Using the tree diagram, calculate the probability of a face card and then another face card. In the tree diagram, we are shown how many times this happens. And so all we need to do is calculate the sample space so we know what to divide the number of times that face cards were chosen twice by. So this would just be 144 plus 480 plus 480 plus 1600, which equals 2,764. And yep, this one reduces. This would be 36 out of 691. Okay, hopefully you got that right. Next problem. Example 3, more practice with tree diagrams. An urn has 3 red marbles and 8 blue marbles in it. Draw 2 marbles one at a time, this time without replacement from the urn. And you guys know what without replacement means. The branches are labeled with probabilities instead of frequencies. The numbers at the end of the branches are calculated by multiplying the numbers on the 2 corresponding branches. For example, 3 11ths times 2 tenths equals 6 1/10. All right, and I've got a little note for you guys here. If you draw a red on the first draw from 3 red possibilities, there are 2 red marbles left because this is without replacement. All right, so using the tree diagram, let's try to find our answers here. The probability of red and then red again, and that is very easy to see here. That would be 6 out of 110. The probability of red then blue or blue then red is equal to 3 out of 11 times 8 out of 10. And it does matter here because we are decreasing the amount. So if blue comes first, initially blue had a probability of 8 out of 11. And then red has a probability of 3 out of 10. So 8 out of 11 if you get brown first, and then red has a 3 out of 10. And that equals 48 out of 110 or 24/55. All right. C, the probability of R on the second, given that you got B on the first. And it shows you B on the first and then R on the second. And you can see this in the diagram. So this would just be 3 out of 10. All right, the probability of R on the first and B on the second. So if R is first, that is 3 out of 11. And then B, if R is first, is 8 out of 10. And that would multiply to be 24 out of 110 or 12 out of 55. And lastly, we have 2 parts left. The probability of BB in the picture. Love it when that happens. This is 56 out of 110. Or 28/55. And I want to add that you can find these by simply multiplying. So it's 8 out of 11, B first, and the second B. So 8 out of 11 times 7 out of 10 is this number. Okay. And then part F, find the probability of B on the second, given that you got R on the first. And the probability of R on the first is 3 out of 11. And the probability of B on the second is 8 out of 10. So the answer, 8 out of 10 or 4/5. All right, let's keep rolling. Example 4, last example, I think, with tree. In a standard deck, there are 52 cards. 12 cards are face cards, F, and 40 cards are non-face cards. So we have the probability of F, the probability of F equals 40 over 52, and the probability of N, the probability of F is 12. Out of 52 face cards, there's not that many. And then non-face cards, there's many more. Okay. So it asks us for A to find the probability of face then non-face or non-face then face. This is an OR probability. And so all we have to do is add them up. And below here, we have 480 of each of them. So since it's impossible to have overlapping events here, this would just be, 480 plus 480, which is 960 over 2,652, and that reduces to 80 over 221. The probability of non-face, given that you got a face, and that's right there, 40 out of 51. The probability that at most you'll get one face card, and in this example, at most one means 1 minus 2 face cards. So it's the complement to us finding the probability of both being face cards. And so the probability of both being face cards is 132 out of 2,652. So we would just subtract. This would be the probability of at most one face card equals 2,652 minus 132 over 2,652. And if you do the math, you get 2,520 divided by 2,652, which reduces to 210 over 221. For the last part, it says find the probability that at least one face card is drawn. So at least one means 1 or 2. And so this is the complement to no face cards or 2 non-face cards. And so we can subtract the probability of 2 non-face cards. So the 2 non-face cards, that probability is 1,560. So this would be, let's use a different color here so we can see this better. 2,652 minus 1,560 over 2,652. And if you do the math, you get 1,092 divided by 2,652, or 7 over 17. All right, that diagrams, is tree diagrams. Now let's move into Venn diagrams. We have our first definition here is a picture that represents the outcomes of an experiment. It generally consists of a box that represents the sample space S together with circles or ovals. And the circles or ovals represent events. All right, so in our first example for Venn diagrams, we're just drawing the Venn diagram. And I like to start all my Venn diagrams off with a box. So I'm going to put a box here. And then we need a circle or oval. I'm not going to call it a circle because they're probably not going to look that circular unless I do this. And then I'm going to make one overlap a little. And then I'm going to draw this line so it looks like you can see it. All right, so I'm going to call this event A and this event B. And the problem says, suppose an experiment has the outcomes 1, 2, 3, all the way to 12, where each outcome has an equal chance of occurring. Let event A equal 1 through 6 and event B equal 6 through 9. Then A and B equal 6. And since A and B equal 6, that's where I'm going to put 6. A or B is 1 through 9. So that means in A, I'm just going to put the numbers that belong here. We have 1, 2, 3, 4, and 5. 6 belongs to both, so I don't put it twice. And then B would be 7, 8, and 9. Now, since this set went all the way to 12, I'm going to let the remainder of the numbers that aren't present in events A and B just be outside in the rectangle. And so these are still outcomes because they're inside the rectangle, but they are not part of event A or B. And that's it. All right, for our next example, I want you to pause and I want you to draw a Venn diagram using this example. Okay, so assuming that you paused and you drew your Venn diagram, you should have, a rectangle somewhere on your paper. You should have a couple circles inside that represent the events. And then it says, suppose that an experiment has outcomes black, white, red, orange, yellow, green, blue, and purple. Where each outcome has an equal chance of occurring, let event C equal green, blue, purple. So event C is, and I need to extend this, green. Blue is actually present in both, so that's going to go there. And C is green, blue, purple, so we need purple still. Event P is red, yellow, blue, so we're going to have red and we're going to have yellow. And then C and P is blue, and that's why it's in the middle. And C or P is green, blue, purple, red, yellow. Now there's a couple colors that are mentioned here at the beginning that if you're not careful, you might leave off. So we need to add black and white inside the rectangle, but not inside either of the circles for events C and P. All right, example 7. Now we're going to use Venn diagrams to find probabilities. And it says 40% of the students at a local college belong to a club. And 50% work part-time. So I'm going to add those in here. So we've got 0.4. And I thought they did a decent job at making the circles scaled so that the part-time work was larger than the clubs, but you don't have to do that. 5% of the students work part-time and belong to a club, and 5% is 0.05. Draw a Venn diagram showing the relationships, and we've got one there. Now let's find our probabilities. If a student is selected at random, find the probability that the student belongs to a club. Well, that's just 0.4 or 0.4. The probability that the student works part-time. Well, that's just 0.5 or 0.5. The probability that the student belongs to a club and works part-time is just 0.05. And the probability that the student belongs to a club, given that the student works part-time, that's just, C and PT, 0.05 over part-time, which is 0.5. If you divide, you get 0.1. And then number 5, the probability that the student belongs to a club or works part-time, and in this case we would sum the two probabilities and then we would subtract the overlapping students, so we would get 0.85. All right. Example 8, you try, and I encourage you, pause the video and find your probabilities. This is the last example. It says, in a bookstore, the probability that the customer buys a novel is 0.6 or 0.6. So probability of a novel, 0.6. Okay. And the probability that the customer buys a nonfiction book is 0.4. Suppose that the probability the customer buys both is 0.2. So the probability of N and NF equals 0.2. Draw a Venn diagram representing the situation. All right, so let's just get our Venn diagram going. Whoops. Need to do a rectangle first, followed by 2 circles. And then I just need to extend one of these. Perfect. All right, so this is going to be my larger, so this is my 0.6 is a novel, so this is my novel event, and then my nonfiction event is a little smaller, that's 0.4, and my combined is 0.2. Okay. Says draw a Venn diagram. We got that. Find the probability that the customer buys either a novel or a nonfiction book, and that's not hard to do because we know that probability right off the bat. That is 0.2. And then for C in the Venn diagram, describe the overlapping area using a complete sentence. Well, the number of customers who go to the bookstore and purchase, or the probability that a customer goes to the bookstore and purchases a novel and a nonfiction book is 20% or 0.2. All right, and then suppose that some customers buy only compact discs. Draw an oval in your Venn diagram to represent this event. And so all you have to do is just add a little oval in here. Now this one wouldn't overlap, right? Because they buy only compact discs. I am your teacher. This is the way. Go do your homework for 3.5 and I will see you tomorrow.